Now that we have built and validated our algorithms in the model in the loop stage, the next logical step is to move forward software in the loop or SiL. In MIL, everything, both the plant and the controller, existed as simulation models. But in SiL, we take a big leap forward. We replace the controller model with the actual software code. The plant model representing the vehicle dynamics remains simulated, but the controller is in its executable form, just like it will run inside a electronic control unit. You can think of it this way. In MIL, we were testing ideas. In SIL, we are testing the implementation of those ideas. During SIL testing, the control logic that was designed using tools like MATLAB Simulink or Stateflow is converted into source code, usually C or C++, using tools such as Embedded Coder or TargetLink. This code is then compiled and executed on a PC or virtual platform that mimics the embedded environment. Sometimes engineers integrate this software back into Simulink using S functions, allowing it to interact seamlessly with the planned model during simulation. So, the key difference between MIL and SIL is this. In MIL, you test algorithms as graphical or simulated models. In SIL, you test the code generated from those models to ensure that what the code does matches exactly what the model was supposed to do. This stage acts as a bridge between design and implementation. It gives engineers a chance to detect issues in code behavior early, before ever flashing it to hardware. By running the actual compiled software in a virtual plant environment, developers can verify that the logic hasn't changed, that the numerical computations are accurate, and the software structure performs as intended under all conditions. One of the major goals of SiL is model code equivalence testing. The code should behave exactly like the model. If the controller code produces different results compared to the Simulink model, that's a red flag. Maybe due to numeric rounding, data type mismatches, or subtle algorithmic differences introduced during code generation. These are things you can't easily catch during later stages like hardware in the loop. So, SiL helps find them early. Another key advantage is repeatability and automation. Since cell simulation run entirely in software, you can test thousands of input combinations automatically without physical limitations. For example, you can simulate a vehicle running at different speeds, road gradients, and payloads, all while running the real control software code that could actually go inside the car. Let's take a simple scenario. Imagine you have developed an ABS anti-lock braking system controller. During SIL, you run your generated ABS software code on your PC and connect it to a simulated vehicle and tire model. You can apply simulated braking forces, change road friction conditions, or even simulate sensor delays and verify whether your ABS code releases and reapplies brake pressure correctly to prevent a wheel lockup. If the wheel speed response from the software matches what you expected in the model, your software implementation is validated. This stage also helps uncover code level issues that couldn't appear in pure modeling. For instance, a data overflow in a fixed point variable or an incorrect type conversion might not show up in MIL, but it will suffer during SIL. Similarly, compiler optimizations, array indexing errors, or timing logic can be evaluated here. SIL environments also make it easier to integrate unit testing frameworks. For example, running Google Test, Polyspace, or Vector Cache for C code analysis while keeping the simulated plant loop active. That's why SIL is often considered the software engineer's lab inside the model based design process. Now let's look at what engineers typically verify in SIL. There are at least 10 important aspects that make SIL such a vital step in automotive software validation. Model to code equivalence, ensuring the generated or handwritten software behaves identically to the design model. Numerical accuracy and data type validation, checking for precision loss, scaling errors, or fixed point mismatches that can affect control output. Algorithm validation, confirming that the software logic still meets functional and performance requirements after translation into code. Memory management. Identifying buffer overflows, underflows, or variable scope issues that could cause instability later. Task scheduling and execution order. Verifying that the order of operations and sampling times in software match what was intended in the model. Fault injection and exception handling. Introducing simulated faults in sensors or variables to test how the software handles unexpected conditions. Communication logic validation. Testing software's handling of virtual CAN or LIN messages to ensure reliable inter-ECU data exchange. Regression testing. Automatically comparing current simulation results with the previous versions to detect any unexpected behavior changes. Performance profiling. Measuring code execution speed on a host PC to estimate how it might behave on the actual microcontroller. Requirement traceability. Ensuring that every software module and function corresponds to a defined requirement or test case. Maintaining compliance with safety standards like ISO 26262. Each of these verification steps ensure that the controller code is robust, efficient, and aligned with its designed intent long before it touches any real hardware. Another big benefit of SiL is that it's hardware independent. Engineers can test a control software of any ECU, powertrain, braking, steering, or ADAS, without needing access to that ECU yet. This decoupling accelerates development dramatically, allowing software and hardware teams to work in parallel. Moreover, SiL allows for early integration testing. Automotive systems are rarely standalone. For example, a stability control system depends on data from the braking and powertrain ECUs. With SiL, multiple software modules can be linked together virtually to simulate system level interactions. This lets engineers observe cross ECU communication and functional dependencies in a safe and fully controllable environment. A key aspect of modern SiL setups is automation and continuous integration. Using tools like Jenkins or GitLab CI, simulations can be triggered automatically whenever new code is committed. This ensures that software regressions are caught instantly, maintaining the reliability of the control software throughout development. For safety critical systems, SiL also supports coverage analysis, checking how much the code has been tested by simulation scenarios. Engineers aim for very high coverage, often above 90%, especially for SiL level software. This provides confidence that the software has been thoroughly exercised under all operating conditions. Additionally, SiL is invaluable for testing fault tolerant software. Developers can simulate loss of a sensor, corrupted data, or delayed messages and observe how the software responds. Does it switch to a fallback mode, trigger a warning, or gracefully degrade performance? Such insights are crucial for functional safety and reliability validation. Another strength of SiL is that it makes debugging far easier than an hardware. You can pause simulations, probe internal variables, log every signal, and visualize every computational step by step. This visibility helps engineers pinpoint issues that might otherwise remain hidden in real time hardware test. As automotive systems increasingly rely on AI based or adaptive control algorithms, SIL environments are also being used to validate machine learning models. Engineers can integrate neural networks trained for perception or decision making into SIL loop, testing how these AI components behave alongside traditional control code before deploying them in autonomous driving ECUs. Now, let's revisit our ABS example to make this concrete. During SIL, the ABS control software written in C runs on your PC. It receives simulated wheel speed signals, brake pressure values, and vehicle velocity data from the plant model. When the software applies braking control logic, the plant simulation computes the new wheel speed and feeds them back to the controller. This loop continues at real time or accelerated speed. Engineers analyze the results, wheel slip, stopping distance, or brake modulation timing, and confirm whether the software is behaving as the model predicted. If everything checks out, engineers gain strong confidence that the software implementation is correct and ready to move to the next phase, processor in the loop, where the same code will run on the actual target microcontroller for the first time. To sum it up, software in the loop testing is all about validating the integrity, accuracy, and reliability of control software in a virtual yet highly realistic environment. It ensures that what you designed as a model truly translates into software that can run effectively on embedded hardware later. By catching implementation issues early, SiL saves enormous time and cost, supports collaboration between software and system engineers, and lays a strong foundation for successful integration in the later pill and hill stages. So, in short, if mill was about verifying ideas, SiL is about verifying implementation. It's where your virtual design first becomes real code and where you prove that this code can truly bring your automotive system to life.